Okay, so now we're going to look at an example number 10 in the packet. So we are doing exactly like we just did in the previous couple pages ago with matching the equations. These are all base E because we just talked about E. So we're matching the equations with their graphs. And so again, for all intents and purposes, you just want to be thinking about E as some number between 2 and 3. And so when you go to try to find the graph, you are just thinking of it as that number. Okay, so let's start with graph 1. We have e to the negative x. So if we think about our basic e to the x function, which we just saw on the previous page, we know it's going to be increasing like this. I know that's not the most beautiful graph here. And it would have a y-intercept at 1, and it's exponentially increasing. So now we know that if we have a negative x inside our function right here, that is going to reflect the graph over the y-axis. And so, and the other way to think about that is you could think of this as e to the negative 1 to the x power, or think of it as 1 over e to the x power. So that would show you that the base now is going to be between 1/3 and 1/2, right? Because e is between 2 and 3, so 1 over e would be between 1 over 2 and 1 over 3. And so that would be exponential decay. So we're looking for whichever graph that matches with, and it looks like actually graph E is going to be our choice, right? So notice that it has a y-intercept of 1. It's decreasing. If I plugged in a certain value, like say I plugged in -1, it looks like it's passing through the point. So this is the point, -1, comma, E, right? 2.718. So that makes sense. So number 1 is going to graph E. Okay, 2, we're looking at negative e to the x. So again, we're starting with our e to the x, but putting a negative sign out front is going to reflect it over, instead of the y-axis, it's going to reflect it over the x-axis. So it's going to be sort of like that, right? So again, if we have to look through our graphs, looks like graph G is going to be our choice, right? See, and so instead of it having a y-intercept up at 1, it's been reflected down to -1. And the point that would have been 1 comma e is now down here at 1 comma negative e, negative 2.718. So it looks like equation 2 is graph G. Oh, and this keeps happening. I apologize. I don't know why this is happening. I have to keep scrolling through the notes from the previous videos. I must be clicking something that I don't know, but okay. So this is going to be graph G. And then we just continue through here. Now, e to the 2x, again, I'm starting with my usual e to the x function, but multiplying by 2 inside the function is going to affect the horizontally, whether it's stretched or compressed. So in fact, the 2 here is actually compressing it by a factor of 2. So instead of it passing through the point 1 comma e, notice that on graph B, it's at the point 1/2 comma e. So in other words, everything is compressed by a factor of 2. So everything is being squished in towards the y-axis and happening sort of twice as fast. So instead of waiting all the way until you get to 1 to get a height of e, you get there by a half. If you had a hard time seeing that one, you could just pick some values to plug in. So notice that if you plug in 1, you're going to get e to the 2 times 1, or e squared. So that's going to be less than 9 because 3 squared is 9, but it's going to be close to that. So notice that the point 1, somewhere up here, e squared is going to make sense. And also, you may just realize that some of these you might struggle with, and it'll be a process of elimination to see which one's left. There's not any others that are really, I take that back. It looks like 8 and 3 are the 2 that are horizontally stretching and compressing. This one's compressing and this one's stretching. So while we're doing that, let's notice that if we look at graph E, this one, it takes, instead of going through the point 1 comma e, so e is like 2.78, it's taking all the way to point till x is 2 to get there. So 2 comma e to get there. So we can see that that one's been stretched out this way and this way. So that's going to be graph F for number 8. Okay, so continuing through now, if we look at number 4, this is taking our regular e to the x, but it is vertically stretching it by a factor of 3. That's going to affect our y-intercept. So we're looking for a graph that has a y-intercept of 3, but otherwise looks like e to the x. So that's going to be this one. See how this passes through 0 comma 3. So that's going to be graph C. 5 is taking e to the x and shifting it left 3. So notice that our y-intercept, instead of being at 1, is shifted left 3. So this has the point -3, 1. That's telling us that this goes to graph D. 6 is taking e to the x and just shifting it up 2 units. So notice that it has a horizontal asymptote up at 2, but otherwise looks like e to the x. So that's the graph A. And then by process of elimination, this one has to be H, or if we just think about it, this is going to be taking e to the x and vertically compressing it by a factor of a half. So our y-intercept is going to be here at a half. So that one's got to be H. So in general, we're just going to be doing our matching here. We see that exponential functions are one-to-one. They have a domain just like with other exponentials of all real numbers. And the range is also positive values. But if we have, as usual, if we do transformations, it does affect the range. So we have to keep that in mind. So, okay, so you're now ready to do homework number 1 on WebAssign, and I am going to assign this and make this due for Monday. So I hope you watched all 3 of these video lectures and are now caught up to speed and ready for homework 1. I'll see you guys on Monday.